So the two-way ANOVA in R. Now we get to the analysis. All right. As mentioned earlier, including an interaction effect in a two-way ANOVA is not compulsory. However, in order to avoid flawed conclusions, it is recommended to first check whether the interaction is significant or not, and depending on the results, include it or not. If it's not significant, you can leave it out, but check it, always check it. We thus start with a model which includes the two main effects. In other words, sex and species, and the interaction, sex by species. And you notice here on this two-way ANOVA with interaction, this model, it's similar, right? I put AOV, that's the command, right? That's a function. Body mass as the Y variable, tilde, right? So we say body mass as a function of, I put sex plus species plus sex, colon, species. So this is one main effect, sex. Species is the second main effect. And sex by species is the interaction. This model is exactly the same as the one we ran before with the asterisk doing the multiplication, but it's coded a little differently because later on when we pull out the results, it likes that better. It does the same thing. And we ran it on our data dat_c, our clean data. And then we can print the model results by using the summary command to show us an ANOVA table. Run this whole chunk, boom, and we get an ANOVA table with our degrees of freedom, sum of squares, mean squared values, F value, P value. So sex, you can see, is highly significant, right? It's a significant effect. That means if you looked at all the species of penguins together, if you looked at all the species of penguins together and you grouped all the males together with all the species in that group and all the females together with all the species in that group, the males and female body size by mass would be different. They're different, right? But it doesn't tell us anything about how they differ within species. This next line here, this next line in our result, species, is also significant. So that says, if you took all the Adelie, males and females, and compared that body mass with all the Gentoo, males and females, and compared that with all the chinstrap, males and females, one of those species is bigger or smaller than the other one, right? One of those species is not like the other. Which one? Are they all different from each other? And we can already tell by looking at the graphs, it looks like one of them is different and the other two don't differ from each other. That's what that line in the results is telling you, is that one of those species is different. Okay, so we know the sexes are different. We know one of the species is different. And this third line, what this tells us is that there's an interaction. Oh, does that mean? Okay, so it's basically saying that the differences between males and females depends on what species, and or the differences between the species depends on what sex. In other words, you'll see this again later on with the graph. If you look at a bunch of penguins, you got all these three species, you got both sexes, and you compared two of them, it might be that, and one is bigger than the other, it might be that one of them is a male and a female of the same species and they're different, right? But it might be that they are a male of one species and a male of another species. But whether or not those males of two different species is different depends on which species it is, right? Some males and females of this different species are the same. You'll see the graph. It'll make more sense. Okay. So which effects are significant? Which effects are significant? all three effects are significant, right? The two, let's even put it like this. The two main effects, sex and species, are significant, and the interaction effect is significant, right? They all matter. Keep them all in the model. Similar to a one-way ANOVA, the principle of a two-way ANOVA is based on the total dispersion of the data and its decomposition into four components. That is, 1, the share attributable to the first factor, 2, the share of the variance attributable to the second factor, and 3, the share attributable to the interaction of the two factors. 4, the unexplained or residual portion of variation, right? Now, if you look up again at the results here, you'll see the sum of squares, right? The sum of squares column shows these four components. The two-way ANOVA consists of using a statistical test to determine whether each of the dispersion or variance components attributable to the two factors studied and to their interaction is significantly greater than the residual component. If this is the case, we conclude that the effect considered, factor A, factor B, or the interaction is significant. So when you look at the sum of squares, you see it's bigger. We see that the species explain a large part of the variability in body mass. It is the most important factor in explaining this variability. The sum of squares is $143,401,584. The p-values are displayed in the last column of the output above. From these p-values, we can conclude that at the 5% significance level, controlling for the species, body mass body mass differs between the two sexes. Controlling for the sex, body mass is different? No, differs for at least one species. And the interaction between sex and species displayed at the line sex by species in the output above tells us that, and here's where you really pay attention, the relationship between body mass and species is different between males and females. Since the interaction term is significant, we have to keep it in the model, and we should interpret the results from that model. If, on the contrary, the interaction was not significant, that is, if the p-value was greater than 0.05, we would have removed this interaction effect from the model. And let's see what that looks like below. Run and save body mass results below. So if we run this here without the interaction, we can see that the results of our model without the interaction are actually pretty similar, but we don't have the interaction term in there, and we need to include it because it's significant. Note that the following code using the LM function works as well and gives the same result. So if we run this mod 3, and instead of using AOV, we use body mass by sex by species. And then to get our results, instead of using the summary command, we use ANOVA on mod 3. This is what we get. Exactly the same thing. Exactly the same thing. So the linear model and the AOV command, the linear regression and the ANOVA run essentially the same test, just using a different function, and you specify the output slightly differently. So you will notice that the structure of the code for a two-way ANOVA is in fact similar, or really the same as for a linear regression in R. And the formula is dependent variable tilde independent variables. The plus sign is used to include independent variables without an interaction, and the multiplication sign or the asterisk or colon sign is used to include independent variables with an interaction. The resemblance to a linear regression is not a surprise because a two-way ANOVA, like all ANOVA, is actually a linear model. Note that the AOV function assumes a balanced design, meaning that we have equal sample sizes within levels of our independent grouping variables. Moreover, AOV uses the type 1 sums of squares, so we can obtain different p-values when we change the order of the variables in the model. So the order in which you enter the values in the model matters with this analysis, because the analysis first takes into account the first variable you put into the model, and then takes into account the second variable you put into the model. So if you had made it species and then sex, it might make species look more important than sex. And sometimes it can change the significance of the model. For unbalanced designs, that is, unequal numbers of subjects within each subgroup, the recommended methods are as follows. And you could read this here. We're not going to go into it too much. Type 1, type 2, type 3 ANOVA. You can read more about it. Pairwise comparisons. This is what we need to get to.